Hello everyone and welcome to this presentation. My name is Jeon Kim and I'm excited to share our research on column-wise quantization of weights and partial sums. This work focuses on optimizing quantization strategies for computed memory architectures, which is crucial for improving efficiency in deep learning hardware. Throughout this talk, I will walk you through how our approach addresses the challenges of SIM architectures and our experimental results that demonstrate its effectiveness. First, let's discuss the overall process of performing deep neural network inference in SIM architectures. The first step involves mapping four-dimensional weight tensors into a two-dimensional matrix. This figure presents an example of image-to-column mapping process where each convolutional kernel is stretched into a column vector. Once the transformation is complete, we need to perform array tiling to ensure the matrices fit within SIM arrays. As you can see in the figure, the quantized weights can be mapped across multiple columns depending on how many bits can be represented per cell. Now, let's move on to how computation is performed within these arrays. Inside each array, inputs are sent through DACs and word lines. Then the multiply accumulate operation takes place, which generates partial sums as electrical currents in each column. This process follows Kirchhoff's current law, allowing efficient analog computation. And after the MEG operation, the generated partial sums must be digitized using an ADC. Since ADCs come with high power and area overhead, it is preferable to use low-resolution ADCs. However, low-resolution ADCs introduce the risk of quantization errors, which can negatively impact model accuracy. To mitigate these errors while still benefiting from low-resolution ADCs, research on partial sum quantization has become increasingly important. So, what's been done so far? We categorized previous studies on fine-grained weight and partial sum quantization into three key aspects. First of all, weight and partial sum quantization granularity. The granularity refers to how elements are grouped and assigned a common scale factor during quantization. The figure illustrates different granularity levels, ranging from conventional layer-wise to array-wise and fine-grained column-wise quantization. The important thing is that weight and partial sum granularity are independently determined, which means they can have different granularities. Second, various training methodologies exist for handling quantized models. Some methods employ quantization array training from scratch, while others utilize a two-stage QAT strategy. Also, post-training quantization is another option where a pre-trained model is quantized afterward. Finally, regarding scale factors, they can be determined using min-max values in the distribution. Alternatively, they can be optimized as learnable parameters during training to enhance model accuracy. Despite these advancements, here's the problem. Although the weight quantization granularity is crucial because low bit weight models set an upper bound for the accuracy achievable with partial sum quantization, previous works didn't apply fine-grained quantization to both weights and partial sums at the same time. They also missed out on using learnable scale factors for both. On top of that, these methods often relied on two-stage QAT or post-train quantization, leaving room for improvements in training efficiency. So, how do we address these limitations? First, we align weight and partial sum quantization granularity at the column-wise level. Second, we enable one-stage quantization array training from scratch, removing the need for multiple training phases. Third, we make the scale factors learnable for both weights and partial sums to improve accuracy. These enhancements allow us to leverage more flexible quantization strategies while maintaining model performance and hardware efficiency. We'll now go through our proposed methodology in detail, covering how column-wise quantization is implemented and how we evaluated our approach through experiments. First, let's talk about how column-wise quantization actually works in SIM. Our proposed method applies column-wise quantization to both weights and partial sums to maintain fine-grained control. The figure highlights an example where the red column has a weight scale factor SWI, and partial sum scale factor as pi. After the MEG operation, the resulting partial sums are formulated as this equation here. So the column-wise quantization ensures that each column is assigned a specific scale factor, which leads to reduced quantization errors. After obtaining the partial sums, they are quantized through ADCs following this equation. As mentioned earlier, the precision of the ADC plays a critical role in determining the overall quantization error. By using column-wise quantization, we can achieve better accuracy while keeping ADC resolution relatively low. This approach allows us to reduce ADC overhead without sacrificing computational accuracy, which is a key consideration in SIM architectures. Finally, to recover the original values, we apply a dequantization step where the partial sums are scaled back using their respective scale factors. So in this red column, the dequantized value comes out as the following equation here, which applies the multiply scale factors to partial sums. What happens if we quantize partial sums column-wise but weights are quantized layer-wise? Then each column gets a unique partial sum scale factor SP1 to SP4, but all weights share the same scale factor SW. And as you can see in the figure, dequantization happens separately for each column. Now, what if weights are also quantized column-wise? Then each weight column gets its own scale factor SW1 to SW4, and this seems like it adds more dequantization overhead because of the more number of scale factors. But the truth is, the number of dequantization operations stays the same as in the former case. Therefore, the takeaway here is that column-wise partial sum quantization enables finer weight granularity without increasing dequantization overhead. In other words, aligning column-wise quantization for weights and partial sums enables finer and more precise control over the quantization process without introducing additional overhead compared to the layer-wise weight with column-wise partial sum configuration. We also built a convolution framework to efficiently handle column-wise quantization. Traditionally, column-wise processing is inefficient due to time and data management costs. So our solution is a unique array tiling method combined with group convolution. First, we duplicate the weight matrix based on bit splits to enable independent access to each of them. Then, we quantize weights layer-wise, array-wise, or column-wise. The quantized weights then go through optimized MEG operations. Here we use a novel tiling method to convert linear MEG operations into convolutional computations, improving efficiency. And finally, partial sums are quantized and accumulated. Previous work used two-stage QAT to deal with granularity mismatches, where layer-wise weight and column-wise partial sum quantization was adopted. In that case, partial sums are only quantized in the second stage of training to reduce training costs. We achieve efficient one-stage QAT from scratch by aligning both weight and partial sum quantization at the column-wise level. This makes training simpler and more efficient by avoiding unnecessary separate stages to handle quantization and ensures consistent optimization of both. To evaluate our method, we conducted experiments on the CIFAR 100 dataset, comparing different weight and partial sum quantization granularities. Our results show that our approach achieves 72.09% top 1 accuracy, surpassing previous quantization strategies. These results confirm that the models trained with our method consistently outperforms those with coarser granularities. In this analysis, we categorize different quantization schemes based on dequantization overhead. The results demonstrate that using finer weight quantization granularity leads to higher accuracy without increasing dequantization complexity. And this highlights the benefits of our column-wise approach in balancing hardware efficiency and model performance. Next, we analyzed 4 different QAT strategies, each incorporating a different combination of weight and partial sum quantization granularity. Specifically, we categorized these into 2 cases. In case 1 and case 3, Both use column-wise weight and partial sum quantization, but one follows one-stage QAT, while the other follows two-stage QAT. Our findings indicate that when the quantization granularity is aligned at the column level, one-stage QAT outperforms the two-stage one with much less training cost. On the other hand, case 2 and case 4, these cases involve layer-wise weight quantization and column-wise partial sum quantization. In this scenario, two-stage QAT performs better, suggesting that a misalignment between weight and partial sum granularity requires a staged training approach to reduce training cost and accuracy loss. To further validate these findings, we conducted a direct comparison between the best performing QAT strategies from the previous slide. The figure presents our method with blue color, where one-stage QAT and column-wise weight and partial sum quantization are applied. And reference 9 strategy is depicted with red color, where two-stage QAT and layer-wise weight and column-wise partial sum quantization are used. Comparing these two, the star markers indicate that our approach achieves the highest accuracy while reducing training cost by 8.61%, demonstrating its effectiveness in simplifying QAT process without compromising performance. This comparison highlights the advantages of aligning quantization granularities to improve training efficiency and model accuracy. So, in summary, we propose a novel quantization strategy that aligns weight and partial sum granularity at the column-wise level. Our method improves accuracy without increasing dequantization overhead, making it more efficient for hardware implementation. Also, by employing one-stage QAT, we enhance training efficiency and remove unnecessary complexities found in two-stage process. To further support research and development, we have made our open-source convolution framework for SIEM architecture available for implementation. And also, you can check out the code on GitHub, and here's the link. Well, thank you for your time and attention.